All right, we're about to start, so please get settled. All right, welcome back to session 7 of this meeting. We're going to start off this session with an invited talk by Adam Reese talking about the Hubble tension and JWST, and I'm going to start your timer.
Okay. I want to thank the organizers for inviting me. It's very humbling to give a talk in front of the people who built this great telescope, particularly the Rikis, I want to mention, since that's the camera we use for most of these results. So I'm going to give a brief review of the Hubble tension, and then I'm going to discuss new results from JWST that are informing us about this. This is work with the SHUES team and collaborators, and I'm going to discuss results in 2 papers, this HST paper from last year, this new JWST paper, which is accepted in the AppJ, and if there's anybody media related, NASA just did a blog, and you can use this QR code, and I think it should take you there. And for those who want to follow along, cheat sheet, the Hubble tension, 0.18 magnitudes. Okay, so one of the great accomplishments of the last 25 years of cosmology has been the development of a standard model of cosmology, lambda CDM. And this model summarizes everything we know about the universe, particularly its composition. But it's humbling to recognize that about 96% of this model is made of unknown stuff, whose nature we don't really understand, particularly dark matter and dark energy, that both have very shallow roots, I would say, in fundamental physics. That is, this is a phenomenological model, and it's used to essentially fit what we see. But it leaves big questions, particularly about the nature of the dark parts. And so therefore, it's crucial to rigorously test this model from end to end. And one of the only ways we can really test the model from end to end is by predicting the value of the Hubble constant from the model and measuring it precisely. So I'm just going to walk you through that very briefly. But we start out with the model as it looks here, vanilla lambda CDM, and we take the most vanilla form that it can have. So dark energy, a cosmological constant exactly, even though we're not sure about that. Dark matter, a cold particle with no interactions, perfectly stable. We don't know those things, but we assume them. And then we vary 6 free parameters in this model to predict the scale of fluctuations in the plasma of the early universe. We then compare that prediction to the angular fluctuations, the spectrum of those. And so you vary the 6 parameters until you get a good agreement between the power spectrum as seen from Planck and the model, and then you use the model as it's now calibrated to predict the entire expansion history of the universe, the dark matter-dominated phase when it decelerates, the dark energy-dominated phase when it accelerates, all the way to the present time when it tells you the value of the Hubble constant that it should have, 67.4 plus or minus 0.5, very high precision prediction. And so a powerful end-to-end test of this whole story is to directly measure locally the value of the Hubble constant by measuring distances and redshifts. And so we set out more than 20 years ago in a project anticipating reaching this point with the CMB, where we wanted a percent level direct measurement of the Hubble constant, leveraging the Hubble Space Telescope largely, and using what were considered the gold standard tools of distance measurements. So that is 3 rungs or connections to make this measurement, and that is geometry, Cepheid variables, and type 1a supernovae. And I'll talk about those in a little bit. I just want to mention this is not, of course, the first effort to measure the Hubble constant. There was a previous generation with the Hubble Space Telescope that successfully reached 10%. In order to reach percent level, we had to redesign the way we made these measurements, and so I want to mention a few of those key things. It's crucial to cancel flux calibration errors along the telescope by measuring, for example, Cepheid variables with the same telescope and instruments on rung 1 and 2, which we do. It's crucial to measure in the near infrared to reduce the impacts of dust. The first generation was primarily in the optical. It is also crucial to use the best quality supernova data, not things from the photographic era of the 1930s, but modern, well-calibrated data. We use the Pantheon Plus sample. It's also crucial to carefully propagate errors all the way from the beginning of the distance ladder to the end to keep track of covariance between data sources with common errors, and to undertake a wide range of analysis variants to see if the results are robust. And finally, I think it is crucial to publicly release the data so other people can analyze it. We've released 10 to the 7 data numbers and codes so you can read that in. And it's at the GitHub site that I showed on my first slide, and it'll come up again later. All right, so I'm going to briefly walk you through the distance ladder if you haven't seen it in a while. There's been great progress in the first rung. The first rung is where you use geometry to calibrate Cepheid variables. And this is done 3 different ways now, with parallaxes in the Milky Way. I'll talk about those. Detached eclipsing binary system in the Magellanic Clouds have become very precise in the last few years. And observations of water masers in the radio in Keplerian motion around the supermassive black hole in NGC 4258. And so you take any one of these, they're good to about 1 to 1.5% precision. The great aspect of them is that they're all independent from each other, and so they provide very powerful checks. So let me first show you the progress that's been made in the period luminosity relationship as calibrated by Cepheids and parallax in the Milky Way. And so in order to play this game, you have to get to 40 micro-arcsecond precision in parallax. We reached it using spatial scanning of the Hubble Space Telescope to measure astrometry and photometry. This was surpassed a few years later by Gaia DR3, which now provides the best parallaxes. So those are the gray points here. And even better is to use the parallaxes of open clusters measured by Gaia, but you can average hundreds of stars per cluster to reach 10 micro-arcsecond precision. In all 3 cases, it's crucial to still measure the photometry of the Cepheids with HST using the spatial scanning because they're very bright sources. And so by the time Gaia reaches data release 4 or 5, we anticipate this will get to about 0.4% in the calibration of the Hubble constant. Alternatively, you can measure Cepheids in the Large Magellanic Cloud to tie to the detached eclipsing binaries. They're far flung, and so we have to use the dash mode with HST. But doing that, you could collect close to 100 Cepheids in the Large Magellanic Cloud. And this shows, as you go from the optical to the near-infrared, how Cepheids become better distance indicators. You see through the dust. You can also de-redden as well, so you can really reduce the impacts of dust. And then the third anchor is the galaxy NGC 4258. There's been 6 major campaigns on this with the Hubble Space Telescope to find Cepheids there. Now some 669 Cepheids. Okay, on to rung 2. Rung 2 is where you look for nearby galaxies within a redshift of 0.01 or 40 to 50 megaparsecs that recently hosted a Type 1a supernova, and you go back and you find Cepheid variables in those galaxies. This takes a lot of work from Hubble, and there's only a supernova in that volume about once a year. And so it's taken 40 years to collect this sample of 42 supernovae in 37 hosts. And even with an optimistic lifetime for Hubble, I don't think we're going to double this sample again. And so this is basically what we get. But it's a very powerful sample for this. We measure the Cepheids in each of these host galaxies. These are the composite light curves of all the Cepheids in each galaxy, which are used to measure their periods and, of course, identify that they are Cepheid variables. And then we measure in 3 colors the Cepheids to measure their period luminosity relation to measure their distances. Okay, so the third step is actually a very famous step. This is the Hubble diagram of Type 1a supernovae. It's been used very successfully in cosmology. So we're essentially measuring the Hubble flow with Type 1a supernovae. We avoid the nearest ones because you would be affected by flows. We don't go out to too high a redshift because the Hubble constant changes, so you have to account for that. So we want to keep it relatively nearby, so redshift 0.02 to about 0.15. And this data comes from the Pantheon Plus sample, which has compiled all the supernova surveys of the last 20 years and cross-calibrated them using all-sky photometry. Also have measured the covariance of supernova data sources, which had common errors. And again, this data is available at that GitHub site. Okay, so you put this all together, you get one simultaneous distance ladder that takes you from nearby out to the expansion in 3 steps. You do a simultaneous fit to this. It's just a series of linear equations. There are 5 free global parameters in the distance ladder. 2 of them are the fiducial luminosity of the standard candles, Cepheids and Type 1a supernovae. 2 of them characterize Cepheid variables, the slope of the period luminosity relationship and the luminosity metallicity dependence. And the last, of course, then is the Hubble constant. So we use some 3,200 Cepheids 300 type 1a supernovae, this non-diagonal covariance matrix, which now for the first time keeps track of systematic uncertainties, how there are dependencies between different data points, and you do the simultaneous optimization, which you could just do by inverting a matrix since this is all linear, or you could do an MC-MC so that you can see the relationship between the different parameters. I hope this isn't too disturbing to anybody, but we don't get the same value as Planck. We get 73 plus or minus 1. That includes systematic uncertainties. You may have heard this before. And this is 5 sigma from Planck. Or if we include the latest cluster data from Gaia, it's more like 5.3 sigma. To really convince yourself, you have to run MC-MC samples out to 100 million samples to check the tails. And indeed, we are 5 sigma from Planck, but with a very good fit internally to the data, as you can see from the chi-square. Okay, so that's the result, the baseline result. Then we go through an exhaustive set of analysis variants, 67 variants of the analysis in 12 different categories, varying anything you might think of or that people have suggested in the literature, from unusual reddening laws to inclusion of tip of the red giant branch to different calibrator samples, different anchors, different ways of clipping Cepheids. These are the main variants that people most ask about, so I sort of show them here. And the value you get from the Hubble constant, you could skip the local region if you thought we live in a funny place for some reason. The bottom line here is it's very difficult for us to get below about 72.5 or above about 73.5. And it's not just us. If you also look more broadly at the community using other distance indicators for pieces of this ladder, and you separate from different ways, different CMB experiments that are predicting the value of the Hubble constant, they cluster around 67 to 68, whereas the local measures of precision are all higher in the 70 to 75 region. There's really no precise local measurement that's coming in lower than Planck. This is what we call the Hubble tension, and it's been around with us for about 10 years. So what is it? I wish I knew. It could be something missing in our understanding of the universe because we use lambda CDM to connect from the beginning to the end. Of course, we also worry whether it could be some kind of systematic error. And so this is a list of about 10 major ideas people have had along the way that the community has done an excellent job of evaluating. And if you go to this QR code link, there's a full literature search and spreadsheet with about 50 to 70 citations that explain, going through each of these, which papers have shown that these are not significant. That's what allows me to draw blue lines through these. What I'm going to talk about in the rest of this talk is number 10, the idea of crowding in Cepheids in the near-infrared, what that is, and what JWST can do about it. So generally, when we look at Cepheids, we are looking at Cepheids in galaxies. We're looking through many other stars in that galaxy. So we're seeing the Cepheids superimposed on other stars, like you see here. Now, you can account for the background, or crowding, as we call it, by just throwing down fake stars in this region to measure the mean amount of this background provided from these stars. That's what we do. And so as a result, it's not a systematic uncertainty, but it is the largest source of noise in our measurements. It's the largest statistical uncertainty. Now, when you have a telescope with higher resolution, and keep in mind these are mostly red giants, so the red end really matters here. When you have a telescope with higher resolution, PSF gets smaller, everything looks like it's further away from everything, and you essentially get uncrowded images. Now, in the past with HST, we found that the data passed 6 null tests of crowding. So we didn't think this was a big issue, but as I said, it is the biggest source of noise in the measurements. So just to put a finer point on this, this is the different sources of scatter in the period luminosity relationship for Cepheid variables. Now, we want to stay away from the blue for our final measurements to get away from dust, but we don't want to go too red because we want good resolution. We want the Cepheids to be bright, to have good contrast. So the sweet spot here is really the near-infrared, but the problem was Hubble has very big pixels, low resolution, so we had large scatter. This is a dramatic improvement with JWST. This is just at a conceptual level that we expected to be able to reduce the uncertainty by a factor of 2.5 to 3. You don't see that too often in measurements like this. So in cycle 1 and then going ahead in cycle 2, we began observing galaxies where we knew where the Cepheids were from Hubble, but following them up with JWST, with NIRCam in 3 filters, FO90W, 150W, and 277W. The key here really is 150W because it's almost exactly the same filter as we use for HST, F160W. So this is going to be a very apples to apples comparison. These are the Cepheids we observed in the first cycle. These two I'm going to talk about. These ones are done as well. We're doing higher background ones in cycle 2. There's also a program from the CCHP that is measuring 10 of the nearest hosts. Now, we observed the Cepheids in 2 epochs because we wanted to check 3 things. We wanted to check the photometric stability of JWST across our measurements with the static stars. We wanted to be able to confirm that they were Cepheids, that we had matched the right star by seeing the variability of the stars. And we wanted to be able to rephase the Cepheids. I'll say more about that in a second. So this was our first set of observations. So this is the first rung on the distance ladder. I mentioned NGC 4258 and NGC 5584, a type 1a supernova host. Here are the Cepheids in each of these galaxies. And Marshall Perrin was good enough to monitor the wavefront of JWST during our observations and show us what kind of hiccups we could expect in our photometry. There were no major hiccups during our observations. Everything at the time of our observations would be modeled to be less than about 5 millimags in the filters we were looking. So this was just not a concern for us. Then we recovered the Cepheids from the positions from HST. So here are color magnitude diagrams. The Cepheids are shown here just where you expect them to be in the instability strip. They're yellow supergiants. They're not red. They're not blue. They're in between, just where we would think. Here are postage stamps of Cepheids. This is just a span of the ones 39 to 43 days in the where they're located, in their optical measurements from Hubble, in near infrared and far infrared from HST and JWST. The thing to really focus on is this comparison. So this is HST and JWST at the same wavelength, what is essentially H-band or 1.5 microns. And the improvement in resolution is dramatic and makes it much, much easier to precisely measure these Cepheids. Then, as I mentioned, we measured them for 2 epochs. And what was great about that was it allowed us to look at the change in the brightness of the Cepheid. So this is difference in between the 2 epochs as a function of period. Now, we separate our observations by chance by about 22 days. So any Cepheid that has a period of 22 days, you're seeing it at the same phase over and over. So there's 0 difference there, but anything else is telling you about the phase that you're observing the Cepheid. So here is the light curve of the Cepheid, and we've color-coded it by phase. And so if you find Cepheids, the delta measurements up here, you know you're on the late part of the light curve. Over here, you're on the early part. This gave us phase constraints that are better than just square root 2 of combining 2 random epochs. This is the most important plot in the whole talk. This just makes me smile. This is a dramatic improvement comparing the period luminosity relationships as seen from Hubble with the gray points versus the red points seen with JWST, both for the anchor galaxy NGC 4258 and the supernova host NGC 5584. It's a factor of 2.5 improvement in dispersion. This is, I think, one of the best examples I've seen of how JWST has improved our ability to make measurements like this. The difference in distance between these is consistent between HST and JWST, which just demonstrates what I said, that the HST measurements were noisier, they weren't biased, and so we get the same difference, but this is why there's such a dramatic improvement. If you just look at these postage stamps comparing them, they're just essentially uncrowded in JWST by comparison. We can actually look at the distance that we get for this galaxy because we've measured both rungs now. And so this is the distance modulus. This is what we measured in the past. This is what we measured more recently with HST. This is what another independent group, the Arcaria project, they went back to the original pixels and tried to remeasure it themselves with different methods, got very consistent answers. And then this is what we're getting with the closest matching band passes with JWST right here. This is what you would have expected if you took Planck and the lambda CDM cosmology and a Hubble constant of 67.5. So this difference is the tension. I think this shows that systematic errors in HST photometry do not play a significant role in the Hubble tension. And if you weren't convinced there, we've done 5 more galaxies that we haven't published yet, so this is just preliminary, but we're seeing the same thing in all of them, this sort of factor of 2.5 to 3 reduction in dispersion, very good agreement with Hubble in the mean, but just far more precise data, which is going to ultimately allow us to refine measurements of the Hubble constant. For now, I'm talking about this as a check, that sort of item 10 that I showed you there. Okay, so getting to conclusions. So this discrepancy, this Hubble tension, it's been around for 10 years. People have looked really hard at lots of different possibilities, different possible sources of error have been studied quite intensely, and no source of error has been found that would explain this. And now JWST, I think, has really kind of put a nail in the coffin of, was there a problem with Hubble's Cepheid measurements? As I said, another way to describe this is when you look at even other measurements, even the ones that are less precise but still relatively precise, they're clustering above. There's no precise one that's coming in lower than Planck. So this is a pretty robust statement at this point. As I said, an exhaustive test of systematics, variations of the analysis. We don't see any sources of excess noise or internal inconsistencies within the distance ladder. Particularly, the results are inconsistent with some of people's favored explanations in the past of dust, metallicity, or crowding as explanations. So JWST has shown that the tension is not due to problems in Hubble measurements. I think that's a very significant contribution to the story. And so I think this is very interesting. I mean, what is actually going on is there's something missing in lambda CDM when we use it to tell the story of the expansion of the universe, really threading a needle all the way from the beginning of the universe to the end. I don't know. Is it new physics? I mean, this is a hard problem because we have very constraining cosmological data. And so it's a very hot topic for theorists to think of extensions to cosmology to explain this. And there have been at least about 1,000 papers on the archive in the last few years that are attempting to do this with varying levels of success or failure. And so I think these results are going to keep people working late on this problem. I'll end there. Thanks.
All right, any questions? Oh, you already got a hand. Let me get to you.
Thanks, Adam. It's really cool to see those errors start coming down. So other than waiting for theorists to fix this, is there any observational experiments that we can do to help the theorists?
So there are ideas that often they involve some change in the universe, particularly at early times, dark matter decaying or early dark energy or some inhomogeneity, a primordial magnetic field. Many of those would leave a signature in the cosmic microwave background at high L, small multipole, or in polarization. And the upcoming experiments from like S4, the Simons array, are likely to be able to see those. More nearby, I think people can be looking at LIGO for additional information, looking at this, a totally different way. It's a hard problem. It's interdisciplinary. I don't want to rule out anything. I mean, even experiments which are going to measure H of Z, essentially the equation of state of dark energy, will be very helpful because, this could in principle be a story about the late universe and dark energy being funny there. We have no indication of that yet, but really better data there would allow you to either completely remove that from the story or, present some kind of smoking gun that could be part of the story.
Okay, give me a second.
Thanks for a great talk. My name is Aklan from University of Florida. I was wondering if JWST galaxies at the highest redshifts, cosmic dawn, epoch can be used to measure their rate of expansion somehow to get some constraints. And
how high a redshift are you thinking?
Like 8.
8. I've yet to really learn of a really good distance indicator in a kind of redshift 8 galaxy. I just think that we don't understand galaxies well enough to be able to pick out any aspect, their luminosity, their size as a distance indicator. People have started looking at quasars. I think that's hard because they have a lot of intrinsic dispersion. But I guess if anything, I would say quasars are probably what people are trying to do that with, maybe up to redshift of about 6.
Other questions? We got about 5 minutes.
We have one online.
Oh, yeah, go for it.
Sure. This is from Ethan Siegel, who asks, there are still many in the community who believe that ultimately all measurements of H naught will eventually converge at around 69 to 70, and all of this tension will go away. What would you like to impress on members of this community who still feel this way?
Yeah, I think that's a great question. I think that there's a tendency for people to look at modern measurements through the lens of history and say, oh, well, you know, there's been differences before and things come out in the middle, and that's just sort of what happens. But what I would like to impress upon people who think that is this is not people measuring the same thing and getting different answers. That's what happened 30, 40 years ago. They were measuring 50 and 100 with the same tools. They were measuring the local expansion rate. This is people measuring something that the model tells us should be the same, but the reality is you're measuring the early universe and a prediction, you're measuring the late universe and a reality. So the difference itself, I don't care what the value of the Hubble constant is. I don't care what it, quote, comes out to be. I want to understand why our best tools, our gold standard tools, are not agreeing with each other, and if that is telling us something about the universe. So I guess I would say people who think that we're just trying to figure out the Hubble constant and, oh, they could just shortcut the process and say it's probably 70 in the middle are sorry, but at some level are missing the point. That the point is, why do these things disagree? Are they telling us that the model we're using is not correct? That's what I think people who are studying this problem seriously want to know.
Questions?
Hey, Adam. Great talk. Mark Postman here. Do you know of any similarly rigorous work on the CMB side to check for calibration or other systematic errors in the data on the CMB?
All right. Yeah, so I would say there's two responses from the CMB community. I'm not in that community, but putting on what I've heard from them. One is they have other experiments. They have WMAP crossed with ACT or SPT that can sort of recover some of the precision and still gets answers around that. And I got to be honest, at some level, CMB people think, you know, the CMB is right. It's the right tool. And this local stuff is, you know, they're skeptical that anybody can measure things with the elegance and precision and whatnot that you can with the CMB. I think you can. I think, you know, HST, JWST, Gaia are just as precise as the CMB. And I think, you know, if people would sort of look at the whole picture, they would see, yeah, everybody's actually measured very well with great precision and redundancy and checks and stuff. So I would encourage people, if you haven't taken this seriously before, that you should.
Time for maybe one more quick question, if there's one. Oh, you're in the middle. Okay. Can we please pass this mic back?
Thank you. Sorry. So my question was, you can kind of see it in this plot, but you had a previous measurements as a function of time where the jump between, with Planck in 2013 looks a bit bigger. So I was wondering what the major thing that caused that sort of discrete jump was.
I don't know.
Okay.
I mean, this was going from WMAP to Planck.
Right.
So that was the first Planck data point. So they've been there from the beginning. Yeah, I mean, it's right. I don't know if there's yes, sorry. Actually, I can tell you. I take that back. So Planck had essentially measured the first half of what we think of as the power spectrum now. Sorry, WMAP had. And that half actually favors H0 more like 70, maybe even 71. The high L half, the high frequency half, which is what Planck gets uniquely, actually all by itself would favor more like 64, 65. And so the two pieces together, you're at about 67. Now, some people have pointed to this as a possible anomaly in the CMB on the sky. Like, how come the same model is actually drifting a little bit in the cosmic parameters as you go to different scales? So, you know, there are various lines of evidence of funnies in the CMB data you may have heard about, like large-scale funnies, the low multipoles, which seem about 3 sigma off of even with cosmic variance. These differences when you split the data set, something called A lens, which is a kind of fictitious parameter that you put in there to sort of soak up any error in the beam, and it should not be detected, and it is. So, I don't think the CMB is without some concerns, but I don't think it's the cause of this.
Great, let's thank Adam again and get our next speaker. Oh, is there like a reverse effect? Turn it off. Great.
Maybe that's the one.
Ooh. Fancy. It's the wrong.
On screen.
Here?
Yeah.
Yes.
That's the one.
I can do this. Okay. All right. Next we have Hakeem, and we'll be hearing about unveiling the faintest galaxies over a high redshift range with JWST.
Thank you. Thank you. Thanks.
I'm going to set 25 minutes here, and so you can keep track.
Yeah, thank you. So I'd like also to thank the organizers for putting together this nice conference and also inviting me to present some of the exciting results we've been having in the last year or so from JWST. I think we've heard a lot yesterday, especially about bright galaxies, and today I'm going to talk about how JWST is helping us unveil and characterize some of the faintest galaxies at the epoch of reionization and beyond. And I also would like to acknowledge some of the collaborators who are doing most of the work here. Great collaborations around large JWST programs here, especially the people highlighted in the blue here, students and postdocs who are doing most of the work. So to put things into context, one of the main science drivers of JWST is to unveil the first generation of galaxies and also understand the process of cosmic reionization. So it's mainly probing this era of dark ages that's following the recombination era. So here we have the universe, which is filled with neutral hydrogen, and then you have the first sources of light, which ionize their surrounding until completely ionizing the universe around redshift 6. So I'm going to talk here about how the HST helped us improve and how HST was instrumental in characterizing the galaxies during the epoch of reionization, and how JWST now is pushing this redshift frontier to potentially the dark ages, and at the same time, how the unprecedented spectroscopy capability of JWST is going to help us characterize exactly this population of galaxies at the epoch of reionization. So through decades of observations, the Hubble Space Telescope has accumulated a lot of deep observations in many fields on the sky. And from these legacy fields, we had more than 1,000 galaxies, 2,000 galaxies identified at redshift higher than 6. And from these large samples of galaxies, we had good constraints on the overall shape of the luminosity function of the luminosity distribution of galaxies and its evolution with redshift. So one of the outstanding questions about this luminosity function now is to know if at the faint end of the luminosity function, the galaxies, this UV-LF is going to break and we're going to hit the limit of star formation, of galaxy formation at the low mass, extreme low mass galaxies. And the other question is, at the bright end of this UV luminosity function, there is still a debate whether this bright end is best described by a double power law or a Schechter function, especially knowing that at these bright ends you will have also AGN contribution in there. So this is more or less the landscape before JWST. And early on, with the first results from JWST, ERS, and ERO data, we had already exciting, surprising results. And we have heard about this at the first conference we had here at Space Telescope. And this is a compilation of the high redshift galaxies observed mainly with HST. So you have tons of galaxies at redshift 6, 7, and 8. And when you go closer to redshift 9, you have fewer and fewer galaxies. And especially here, you have only a couple of galaxies at redshift higher than 10. And now you will see a new compilation of JWST, and you will see how remarkable we're detecting many and many galaxies at redshift higher than 9. And you can visually appreciate the redshift shift that JWST is bringing here. So this is an example of these high redshift galaxies from the Sears survey, where you see this galaxy that's been detected at redshift 8 with HST in a few bands here, faint detection, and it has marginal detection with Spitzer, and you see how it's detected, well detected, strong detection in JWST filters, many filters actually, and this is in less than 1 hour of NIRCam observations. So this is how JWST is changing the game of high redshift galaxy studies. And in this context, I want to talk about our Uncover survey, which is targeting one of the frontier field clusters, Abel 2744. Uncover has two components. It has one ultra-deep NIRCam imaging on the center of the cluster here with nearest parallels, and the second component is a NIRSpec follow-up with multi-object spectroscopy. And this cluster is very nice because it has Muse spectroscopy, which helps a lot to model the lensing effects in this cluster, and has also lots of HST ancillary data. So this is the mosaic, the Uncover mosaic that's been released a few months ago. So you see here the mosaic coverage in addition to the glass coverage and a DDT program here. And you see the main lensing structures here. And if you overlay the lensing magnification, here you see contours of magnification from 2 to 100. And you see these three substructures, lensing substructures here we are interested in. And if you put here this into context compared to other surveys, you will see here in terms of depth versus area that Uncover is here, but with the lensing, you're going to reach intrinsic depth of 31 magnitudes. So this is the main advantage of probing or targeting these lensing clusters, of course. So now I'm going to present a few of the results we are getting from this survey. So first of all, we have identified about 20 galaxies from redshift 9 to 13. So we're using here a dropout selection, so selecting through the Lyman break in these galaxies, so isolating this color window to avoid contamination from low redshifts and low redshift galaxies and stars. And we're also combining this with SED fitting, where we are computing photometric redshifts using different SED fitting tools. And you see that with all the JWST data, we have very narrow photometric redshift solutions and a good agreement between the different SED fitting codes. So we are doing a careful photometric selection of these high redshift galaxies. So this is the distribution of all these galaxies in the field. And these galaxies have absolute magnitudes between -18 and -20, so still relatively bright for those redshifts. And from that, we can also compute the UV luminosity function. So this is a work led by Irina Sheverinska. She has a poster, so you can check it out about these results. So these two people have been doing a careful modeling of the lensing effect, of course, in these clusters. For instance, if you look at this is the source plane, actually, we're looking at redshift 9. So you see the dramatic shrinking of the area you're surveying from the image plane to the source plane. So you have to take into account all these lensing effects in the survey volume and detection of galaxies. And this is the result of the UV luminosity function in blue here. And you see that we are also confirming this trend of an excess of bright galaxy. So this is a factor of 10 or 100 to 100 higher than theoretical predictions and extrapolations from low redshift studies. So I think we've seen this a lot, so I'm not going to go into details. So these results go along the lines of the excess also in the star formation rate density of those redshift at the bright end. And of course, many explanations and scenarios are explored to explain this excess. One of them is, of course, the obvious AGN contamination and also the low redshift contamination of these sources. So that's why we have the second component of Uncover, which is the NIRSpec follow-up to get spectra of all of these sources. So you see here all the targets that are put in the MSA design. So we have ultra-deep NIRSpec prism spectra of about more than 500 targets, 7 independent pointings with the MSA, which translates into an exposure time ranging between 3 and 19 hours. So the first part of this target selection is, of course, the high redshift galaxies. So you can see here the results of this follow-up of these high redshift galaxies. We have confirmed 10 galaxies at redshift 8.5 to 13. And you see here the beautiful spectra, a clear detection in the continuum, and even rest frame UV and optical emission line, and a strong Lyman break here you see in these galaxies. And one of these galaxies is around redshift 13, which is the second highest redshift galaxy confirmed with spectroscopy. And we've been wondering also about how robust are the photometric selections of this high redshift candidate. So I can tell you that we had 100% confirmation rate of these dropout candidates at high redshift. So the selection is pretty robust, I can say. And here in this plot, the MUV versus redshift plot, you see how this uncovered spectroscopy adds to the sample of spectroscopic confirmation of high redshift up to a redshift of 13. And it turns out 2 of these sources are actually have AGN signatures, either through broad H-beta emission line or high ionization lines or even X-ray detections. So from that, we can also compute or measure the contribution of AGN to this UV luminosity function at high redshift. So you can see here the results in red, here the 2 AGNs. And you see that these are, of course, are lower limits, but you can see that it's a bit higher than the previous estimate of the AGN luminosity function here on number density of AGNs. And one of these AGN actually is a paper by Vasily Kukarev, which is in the audience as well, so you can check out that paper. And 2 of these AGNs actually show also emission lines blueward of the Lyman break here. You have an emission line of Lyman alpha emission line which is transmitted through the RGM, which indicates a giant ionized bubble at redshift around 8 here, 8.5, where the 2 AGNs are the center of the galaxies. Of the ionized bubble, sorry. So now going back to this, we can take a step back and reflect on this sample of high redshift galaxies, and we can realize immediately that most of the galaxies, if not all of these galaxies, are relatively bright. So here from the imaging, the high redshift candidates, they are all brighter than -18. And on the spectroscopic side, at the epoch of ionization, so a bit lower redshift, it's not really much better. You have only a handful of galaxies fainter than -18. So this is why well, I was talking also about this luminosity function before, that you see at the faint end how the luminosity function is very steep. It means that faint galaxies is the dominant population at those redshifts. This is why faint galaxies are believed to be the major actors of cosmic reionization. And this is why we put highly magnified sources at the epoch of reionization in these MSA masks. So I'm going to show you the results of the spectroscopy of the highly magnified sources. So remember, these are the deepest JWST spectroscopic surveys that reaches close to -17, and this is our spectroscopic sample. So we are really probing a different parameter space, different population of galaxies that's never been seen at the epoch of reionization with spectroscopy. So here are the galaxies we are targeting. You can see tiny galaxies in the slitlets here. Some of the galaxies are actually arcs because of the strong lensing that's offered by this galaxy cluster. You can see that all the galaxies here are in the high magnification region. So there are the beautiful, amazing spectra of these very faint galaxies at the epoch of ionization. So here we're talking about galaxies that are, the intrinsic magnitude of this galaxy is 31. So this would be impressive already for imaging, so let alone spectroscopy. So you see H-alpha, O3, Balmer lines, Lyman break in these very faint galaxies at the epoch of ionization. This galaxy has exposure time of 17 hours with near spec. It has an amplification factor of 26, which gives you an absolute magnitude of -15.5. This is crazy. And this galaxy has a stellar mass below 10 to the 6 at redshift 8. This is comparable to local dwarf galaxies. So we've been talking about how JWST is amazing. This is just silly. This is so from this, we can also now compute the spectroscopic luminosity function. So you can see the result here of the orange point. We are confirming the photometric luminosity function. We are confirming that this high abundance of low mass ultra-faint galaxies at the epoch of ionization. This is also due to the fact that we have also nearly 100% confirmation rate for also these galaxies at the epoch of ionization. So the second important result is that we can now measure directly the ionizing efficiency of these galaxies at the epoch of ionization. Until now, we've been doing this at redshift 2 and 3 in local analogs to measure ionizing efficiency. First time we can do it at the epoch of ionization for ultra-faint galaxies. And these 2 points are galaxies brighter and fainter than -16.5 in absolute magnitude. So you see that the fainter galaxies have an ionizing efficiency factor of 4 higher than canonical values assumed for massive galaxies here. So it means that these faint galaxies have a very high ionizing production rate. And if you combine these two pieces of information, you can measure the total ionizing emissivities of galaxies and see if they can reionize the universe. And of course, this is what we did. And here you have the total ionizing emissivity for galaxies as a function of the integration limit in MUV. And you see here, when you account for these faint galaxies, the total emissivity is actually higher than the threshold where galaxies can reionize the universe. Most importantly, you need only modest values of escape fraction to do the job. For only 5%, you can actually already reionize the universe with these galaxies. Moreover, if you look at the properties of these faint galaxies, you're going to see that they have young stellar ages. They have very blue UV continuum slopes. They have low stellar masses, as I showed 10 to the 6, and low metallicities as well, and small sizes, which leads to high star formation rate surface densities. All these properties and parameters are indicative of high escape fraction of ionizing photons. So when you combine all these pieces of evidence, we can say that we demonstrate that galaxies were actually the main drivers of cosmic reionization. So now, looking ahead, on the imaging side, we still, as I showed, we are still missing also on the imaging side the faint population, a lot of population, dominant population of galaxies. And I don't like that. So that's why we have in Cycle 2 a large program called GLIMPSE, ultra-deep near-cap imaging of another frontier field cluster, Abell S1063, to push even deeper to 31 magnitude in imaging, which with the strong lensing translates into above 33 intrinsic depth in imaging. So these are the deepest observations ever obtained on the sky. So we'll have 7 broadband filters covering the whole spectral range from 0.8 to 5 microns and 2 medium bands. So remember, these were the bright galaxies we have been detecting, and we've been missing, of course, this dominant population, and also our estimate of star formation rate density at early epochs is biased, of course, towards massive galaxies. So to get a complete census of the star formation rate activity and density of those epochs, we need to account for those faint galaxies. And of course, if you want to look at the first generation of galaxies, and the POP3 stars, and understand the formation of the first galaxies, those are unlikely to be massive galaxies. So you better look at the faint galaxies. And one of the main science goals of this program is also to understand the feedback, mainly stellar feedback, that regulates the galaxy formation and the galaxy growth at early epochs. And this is mainly reflected in the low mass galaxies. This is why when you look at this UV luminosity function predicted by different theoretical models of galaxy formation and cosmological simulations, you see that they start to all disagree at this faint end, because it depends mainly on the feedback recipes, on the subgrid physics you are putting into these simulations. And these simulations have never been confronted to observations in this luminosity regime. And that's because this is the current limit of the imaging surveys we have even with JWST. And GLIMPSE is going to explore this regime. We're going to put strong constraints and tests for the galaxy formation models by robustly measuring the abundance and the shape of the UV and luminosity function here. And if you are still not convinced about the benefits of lensing, I'm showing here the comparison of what you expect in terms of number counts of these galaxies with lensing and without lensing. So you can see here in the blank fields with dashed lines, and the color fields are the lensed fields. So we're expecting hundreds of galaxies fainter than -16 with this program in lensed fields, and we would expect 0 galaxies fainter than -16 in blank field. So the only way to do this is really to do lensing fields. And I still have maybe a minute yet. So I just want to mention also on the bright end of the luminosity function, there are many programs also trying to put constraints on the bright end, Cosmos Web, Primer with JWST. But if we want to explore these really bright and very rare galaxies, you need tens of square degrees on the sky. So this is what we can do also with Euclid, which is very complementary to JWST, a nice synergy where we have a deep survey with Euclid covering 53 square degrees in 3 fields here, and we expect to detect thousands of galaxies brighter than -21 to -22, as you can see here. So this is going to be a lot of data coming to constrain both the faint end of the luminosity function and the bright end. So I'm going to leave you with a summary. This summary slide could have been just JWST is awesome. But I decided to add some text here. And yeah, so I'll leave you with this summary. Thank you.
Thank you for another excellent invited talk. Questions? Yes, immediately.
Thank you for the great talk. So for the faintest galaxies to be seen in the lensed frontier fields, how much uncertainty do you expect from, say, different lensing models to constrain the luminosity functions?
Yeah, so the frontier field cluster is, the lensing model is really well constrained from frontier fields data. And you can see that these galaxies are actually in the frontier field area. These were selected already in frontier field data photometrically. So the lensing model is great in there, and we also include all the lensing uncertainties in all the parameters I showed.
More questions? Yes.
Hi, Hakeem. Great talk. The evolution of massive stars must be very, very different at these redshifts than what we know locally. But that's key to interpreting a lot of the observables and turning them into physical parameters like star formation rates, et cetera, et cetera. I mean, you showed some beautiful spectra where you can see 4363. Did I see that? I mean, what do we,
It's blended, but it could be there, yes.
What can you say? What do we know about how different massive star evolution is to inform the way we translate observed properties into physical properties at this redshift at this point?
Yeah, I mean, in terms of course, SFR and all these parameters, I agree with you. IMF and everything would affect that. And for the ionizing properties of this galaxy, we actually compared to the model, BPAS models and everything. And we are getting really close to the maximum ionizing efficiency you would get from these most massive stars in those galaxies, which would be around 26, really, out there. So I think at some point it's hard to tell which of these models would agree best if you change the IMF, if you add binary stars, if you add, but at least for the ionizing properties I'm talking about, I'm not talking about the SFR or anything in this paper, for instance. But the massive stars would play a significant role in this ionizing properties. Yes.
More questions? We have about 5 minutes.
Great talk, Hakim. This is Roger Windhorst from ASU. So at what point at the faint end or luminosity function with these kinds of, these very decent escape fractions, do we have to worry about overproducing the ionizing budget in the sense that the
That's a great question.
The
Yes.
redshift 7.8 Planck number is in tension, to use that word.
Yeah, I agree. I think at some point, I think we made this kind of estimate, and I think this luminosity function needs to flatten or break down around -13 to avoid that. And I think if you keep this luminosity function very steep beyond that, you would have a second problem, is that you would overpredict the number of low redshift satellites or dwarf galaxies in the local universe. Yeah, so I would say -13. Yeah.
You pass this back.
Very nice talk. I was wondering whether you can comment on in the table that you were showing for galaxies.
The table?
Yeah. This one. There is a factor of 10 to 50 discrepancy between two star formation rates.
Oh, sorry. Yes, one star formation rate is from the SED fitting, and the other one is from the H beta emission line. It's directly for the SFR-UV is averaged star formation rate. The other one is quasi-instantaneous star formation rate indicator from H beta.
So can I take it as indication that star formation is very bursty?
Yes, exactly. So if you look at these ratios, you see that it's much higher than, say, continuous star formation. Yes.
Thank you.
So on your models, if you go back to the other slide with all your models at the faint end, that you say glimpse may help like disentangle between. Are you going to have enough, a small enough error bars to disentangle between all of those? I see only one that is really far from the other one. The rest are quite.
So I'm not showing this here, but yes, we have an estimate of all the error bars because we had to estimate the lensing model's uncertainties. And yes, within the error bars, you can disentangle them between most of these models. Yes.
All right, last question.
Good. Do you think glimpse can help in constraining the faint end of the AGN luminosity functions? Is that something that you're thinking about?
From the imaging, yes. Then we'll need to confirm also those AGNs with spectroscopy. And this is what we are doing. Actually, we selected, there will be a paper coming out soon by Jenny Green and collaborators from Uncover, where we selected AGNs from imaging. They are known now as little red dots. And about 70% are confirmed as AGNs. So apparently you can also robustly select AGNs from imaging. So the answer would be yes. Yeah.
All right, I'm so sorry. Let's think Hakim again. Find him at the next coffee break. All right, next we have, can you load next speaker? Load next speaker. You know what I mean? Yep. There we go. All right. All right, so next we have Jane, who will be speaking about what's going on inside of star-forming galaxies. I have 12 minutes here. I can also give you a warning if you want.
Okay, thank you. All right. Hello again. Everybody good? So that was a lovely talk to go before, because I don't have to explain much about why lensing is really interesting or important in the big picture of understanding galaxies as one of in the wedding cake, one of the deeper ways to probe galaxies. Instead, what I get to do is jump into a piece of that and motivate why we want to do IFU studies of galaxies with lensing. And so, of course, gravitational lensing brings two things, depth, which we just heard a lot about, and also spatial resolution. And so for the rest of this talk, it's the spatial resolution that I want to really dive into, because it's the one where if you're not dealing with lensing, you're just going to be stuck with the diffraction limit, even though the diffraction limit is a factor 2 better in X and Y than we promised. You're still at like 250 parsecs for distant galaxies. That's just what you're stuck with. And if you're not satisfied with that, and you would rather probe individual star clusters, the real pieces of galaxies, and you want to be at tens of parsecs, then you need to go to lensing, right? And so that's why we want to motivate the rest of what I'm going to talk about. This is a reconstruction to motivate that from Hubble from a few years ago, finding just popcorn of stars forming all over this galaxy, almost none of which you could see without lensing if it weren't lensed. And happily, this object will be observed in cycle 2. So, all right, great. We want to do tens of parsec scale studies of galaxies to study the star formation and see what's going on. Okay, great. Well, if it's spatial resolution you want, and you don't want to stick it down a slit, you would like the IFUs so that you get that 2D information. We have 2 IFUs on board JWST. You can use near spec, near infrared, or MIRI MRS in the mid infrared. And so these are examples from cycle 1 from the templates program that I'll talk about in a bit, but showing that yes, indeed, that works beautifully. A lens galaxy at redshift 1.3, where you see H alpha and then the ratio to Paschen alpha really beautifully. And then in the right, smoke at redshift 4, that's a PA feature at redshift 4.2 from a lens galaxy making a lovely Einstein ring. Okay, great. So as one of the ERS programs, the early release science programs, for cycle 1, we put together a program with the tortured acronym templates, targeting extremely magnified panchromatic lens arcs and their extended star formation, which was basically a, hey, let's look at 4 of the brightest, best known lens galaxies with the IFUs as well as the imagers because it's cheap, and really try to understand both what's going on in terms of the star formation and how do we make the measurements? How do we deal with IFU data with JWST? So the science goals were let's see what the stars are doing. Let's map the star formation on the spatial scales of tens of parsecs. Let's compare where the old and the young stars are and understand how star formation has changed with time. Let's figure out how to measure star formation by comparing multiple diagnostics of star formation and seeing how much they vary as a function of extinction and other things. And then let's just measure the physical conditions of star formation, all of the lovely diagnostics of density, temperature, ionization, primary metallicity, and in particular how they vary spatially and how much of that spatial variation you miss when you're studying unlensed galaxies. And in fact, you can fool yourself because you get averages of multiple regions that aren't representative of actually any real region. Okay, so this is the family portrait of templates that one of our fearless colleagues, Kedar Fadki, put together, showing at the top, this is the NIRCam data, and at the bottom, the MIRI data for templates. These are 4 lens galaxies, redshifts of 1.3 to 4.2. Just to pick on one of those, the highest redshift one, we have a paper that's been submitted on the stars, the continuum from that galaxy, showing that there's this blue companion that is interacting with this large millimeter galaxy, but does not seem to be elevating the star formation. So it's an interesting result. We have the middle panel is a paper by Justin Spilker with that PA feature. This is the most distant detection of PAs. And interestingly, the PAs are not where the ULMA continuum is. So the large dust grains and the small dust grains traced by the PAs are in different places. So that's part of the complexity of pulling these galaxies apart on better spatial scales than we've ever seen, is that they don't behave the way you want them to. And then the far right, a paper that Kedar is preparing on the Paschen alpha. We have Paschen alpha for all of these galaxies, so we can measure the extinction. We can measure the star formation in a very extinction robust way, just from Paschen extinction corrected Paschen alpha. So that's where Paschen alpha is in this galaxy, and the extinction in this galaxy is the AV is it's greater than 5. It's very highly extincted. Okay, I talked about this a little. I just said that in words, but here it is in the plot. The ALMA continuum is not necessarily where the PAs are. In fact, the ratio of POS to the big dust grains, it's a factor of 1,000 in luminosity. So the POS are doing something very different than what the larger dust grains are doing. Paper that's just been accepted by Jack Birkin, looking at the metallicity of the 2 submillimeter galaxies in the sample. At the top, in the left panels is H alpha, middle is N2, and then the ratio gives you the N2 H alpha metallicity with the caveats that has. But the result here is that this is, by the way, this is the first time that the rest frame optical has ever been measured for submillimeter galaxies, right? We've never been able to measure it because their extinctions are absurd, but JWST is so sensitive that you that you pull it right out. And in fact, so not only is this the first detection of rest frame optical light from submillimeter galaxies, first measurement of their metallicities. The metallicities are coming in above solar for these 2 galaxies, even if you liberally flag the parts of the galaxies that might be contaminated by AGN. And Jack was, that's a little bit of a throwaway in his paper because Jack didn't care about AGN as much as I did, but I wanted to show you both the quality of the data and the AGN booming out of this one galaxy. So this is the way Jack plots these things, where the color coding is signal to noise in H alpha plus N2, just showing you where the galaxy is the brightest. And then there's a little tiny thing, which is the H alpha plus N2 spectrum for each panel, right? So you can, Taylor and I have spent way too much time geeking out about these kinds of plots, but they really give you a sense of how much information are in these IFU data cubes. And then if we blow up the part that I just, see only the part that I framed here, you can just convince yourselves that these N2H alpha profiles, they're narrow, they're narrow, they're narrow, narrow. Okay, they're broad. That's the AGN. Fine. Well, we didn't know there was an AGN in this source, and I'm a bit surprised that the way that it pops out is in the rest frame optical by yelling at you with its broad H alpha N2, as well as an N2 H alpha ratio that's really large. Okay, so not only can we find the rest frame optical in these galaxies, but we can see where the AGN are, and we can measure the physical conditions, which Jack does in his paper quite well. We can also measure the ionizing, the C-ion, the ionizing photon production efficiency, which we just heard about from Hakeem. We can measure that in these galaxies as well, a paper in prep by Kyun-Ho Kim. We can also measure the ionization conditions spectacularly well. So this is just showing that we have signal to noise to burn on these. And you can measure 5-7H beta quite well. So that's a paper in preparation. We also spent a lot of time, I believe, beating the near spec data into conformity. There were some real surprises, and like a lot of teams, we've been working to understand how do we get these data to behave properly. There are some excess noise issues that meet requirements, but they're just annoying if you're doing near spec IFU data, but you can make them go away. So this is a before and after correction. Detector wizard Bernie Rauscher has come up with this beautiful scheme that corrects this noise, which is actually millikelvin fluctuations in the readouts for the detectors that causes this. We just make it go away, and then the spectra are so much nicer to deal with. So if you care about that, these are the links to go run NSClean on your data as well, and you may very well care for any near spec deep data, IFU or not. Real quick, Sunburst Arc. This is one of my favorite galaxies, probably the best example at any redshift, including redshift 0, of a galaxy that is leaking ionizing photons. And it is highly magnified. You see in Lyman alpha indications that there is light coming straight out towards you with no redshift or blue shift. That hints that there are channels through which ionizing photons can escape. We know that well. We've seen the ionizing photons at the right there from HST, paper by Emil Rivera-Thorson, and Kyun-Ho Kim has shown that you can see. You can measure that the UV slope for the leaking part of the galaxy is much, much bluer than for the rest of the galaxy. Good, and it has higher ionizing conditions. And also the leaker is driving a strong wind, a paper by Ramesh Manali, that the rest of the galaxy is not. Okay, so the JWST spectra, so that's what it looked like for HST. We can reconstruct the lens model. There's a lot going on. Very quickly, for JWST, there's a program led by Emil Rivera-Thorsen. We have the data in hand. We have 3 IFU pointings in the 3 regions that right there that in the rest frame, in the source plane are probing those regions. So those squares that we image map to these squares reconstructed in the source plane. And you can see just the beautiful data that we're working on where there's velocity structure. We're seeing what looks like rotation, and then ridiculously good oxygen 3 telling you about the outflows and the physical conditions. All right, last thing. So this is part of a family of IFU programs that are happening in cycle. This was from cycle 1. Templates is from cycle 1. This is the last cycle 1, and then I'll have 10 seconds to talk about cycle 2. So this is a Redshift 5 galaxy, one of the most massive galaxies known at Redshift 5, discovered through cool lamps. Gaurav Colors, the PI of that program, to help wake you up. We've been calling it the Mike Wazowski arc for kind of obvious reasons. And now, please don't sue us, Pixar Disney, Pixar, thank you. So the Mike Wazowski arc in JWST looks like this. This is the imaging data. It's just gorgeous. You can see the spatial resolution and how much the source is varying within the galaxy. And the spectroscopy is coming. The real ambitious thing that Gaurav is doing here is to do SED models on every single piece of this galaxy, integrating both the spectroscopy that we're getting and the imaging data to really pick apart the star-forming history of this thing. So that program, I can't wait to see. And then we have we have 2 cycle 2 programs to do this, but to take it to the next level, to really integrate the imaging and the spectroscopy to get a self-consistent picture of how these galaxies, in a spatially resolved way, have formed their stars. So that's 2 programs. The PIs are Michael Florian, Gaurav Color, and Matt Bayless. We've combined those 2 programs in terms of how we're going to be reducing the data and dealing with it in order to get these ages and stellar masses for each part of the galaxy, so for the whole thing. And we're calling that LEGOS, another terribly contrived acronym. So please look for those data coming soon. And then I will, so I can't wait to get spectra for every one of these little knots and see how different their star-forming histories are. So thanks for listening. I'm done.
All right, so we're actually a little ahead of schedule, so that was perfect. So we have time for a few questions. So any questions? Yes. Oh, okay. Yes, please pass this.
Hi, Mason Ruby from the University of Memphis. I was wondering, can you go back to that earlier slide where you show the data cube towards the beginning?
Oh, Jack's
I wasn't sure which, is that Passion Alpha or?
That's H alpha.
It's H alpha. Okay. It looks kind of bimodal at the AGN. So I was wondering if you detect like an outflow or anything in that region.
Yeah, there's clearly an outflow.
Yeah,
yes.
yeah.
And this is, yeah, there's clearly an outflow. And in fact, at the last, in July at our collaboration meeting, we were arguing whether that's interesting enough to write a paper on. And if so, who could we con into doing it? Because the data are just so rich and you have to pick which papers that you want to write a thing about. But yeah, there's clearly, you can scan through this and yeah, you picked it out from the 6th row. Yeah, you can just pick out the outflow coming out of this thing. For the sunburst arc, that's going to be a really interesting, if I go forward, for the sunburst arc, the outflows are also kind of screaming at us. That's something we had meticulously pointing by pointing with Magellan Fire, and now we can just do the whole thing, and that will be a fun paper too.
All right, one more question, maybe a quick one. Awesome.
Is the Lyme alpha profile for this consistent with the outflows?
The Lyman alpha profile consistent.
Yeah.
So Emil is working on that paper with a student right now. And so yes, we want to integrate the Lyman alpha, which we have through many nights at Magellan for this galaxy for multiple pointings with the H alpha that we have from JWST, which also gives you a production. Yeah, so that is work ongoing. Yes.
Okay, let's thank our speaker again. All right. Get it going? You want to test it?
Cool. Is this working?
Yeah,
Everyone
great.
can-
Okay,
Sweet.
next we have Brian. We'll be hearing about spatially resolving the distant universe with JWST.
All right. Thank you. And thank you to Jane and Hakeem for doing the hard work of introducing lensing, so I can breeze through that part a little bit. I'm going to be talking about some more awesome spatially resolved lensed galaxy studies that we can do with JWST. Clicker. There we go. So this is very similar to what Jane just showed, but one of the wonderful things that we can do with lensing is get a huge boost in spatial resolution. This is that same galaxy, SDSS 1110, with the source reconstruction. And I also like to show this deconvolved back to what you would see with just HST or just JWST in those two panels on the right. You can really just see how all of those tiny little clumps of star formation just get washed out when you don't have that boost in resolution from gravitational lensing. So taking advantage of, we call these like our cosmic telescopes, taking advantage of this lensing effect really gives us a huge amount of access to these small scale regions that we don't normally see in field galaxies, which can let us really, pick apart what's going on in these galaxies. Jane also introduced the templates ERS program. I won't revisit all of this, but I do quickly want to point out just a couple more results. Jane mentioned Taylor's been working on a paper doing ionization conditions, and in particular this beautiful O3 H-beta map. You can already see the spatial variations here with this multiply image clump on either end of this banana showing a much stronger O3 emission than what you see in the middle, which is really exciting. We can also start playing these games with additional measurements. So the plot on the right is showing O3 4363 over 5007 spatially resolved. So not only are we getting this aurora line in this galaxy at about redshift 1.3, but we're able to spatially resolve it. We can start seeing, this is still a pretty preliminary plot, so it's still a little bit messier than what the final version will be, but you can already start seeing some of the spatial variation in the aurora line. So really exciting spatially resolved work that we can do here. And then just for fun to get a little bit more signal to noise on some of these aurora lines, we can take that IFU cube, smush it down into a single spectrum, and get a huge boost in signal to noise. And with that, we get actually multiple aurora lines in this particular galaxy. So you can see, I believe this is the laser pointer. Yep, O3 4363 now has very high signal to noise here. We also have a faint detection of sulfur 3, 6312, and then the O2 doublet at around 7320, 7330. What's really exciting with this is that we can actually then, using especially those two oxygen aurora line detections, get electron temperatures for the different ionization states of the gas, the O2 and the O3, independently, so we can get a much better sense of the abundances and physical conditions within the gas in this galaxy. So really exciting that we can get all of this awesome information with JWST. I'm going to jump now from templates to higher redshift. So this is the sunrise arc. This is at redshift 6. So a pretty big jump from, around redshift 1 or 2, cosmic noon. Now we're at redshift 6. What was previously considered high redshift, though after the talks yesterday and earlier today, it's kind of middle of the road. No one really cares anymore. Yeah. So with Hubble, we were able to detect this beautiful red arc here. And we were able to measure that some of these clumps are down to radii of less than 10 parsecs. So this is an extremely magnified galaxy. And we're already able to see with Hubble that this is peering down to the sort of very base units of star formation in the distant universe, just at the end of the epoch of reionization here. JWST, if we go, there we go, gives us a more detailed view. So with Hubble, we essentially were able to get a similar image to what you see on the right, just the rest frame UV, where everything looks pretty consistent. But once you go to those longer rest optical wavelengths, you start seeing some really exciting things. In particular, the green band here is straddling O3 and H beta. And you can see some of these smaller clumps over here are showing very little evidence of strong emission lines, where this star-forming complex that we have multiply imaged at the other end of the galaxy is showing up bright green. And same thing here in the middle panel. The red now is the F444 filter, which straddles H alpha. You see the same thing. Very little evidence of an emission line here, and yet these things show up bright red in this particular color image. So what are they? Okay. So, we're starting to see evidence of different stellar populations within this galaxy. And not only do we have NIRCam for this, we also have NIRSpec. Come on, there we go. So this is NIRSpec MSA data. We did not get the IFU on this galaxy because it is too big and too faint to easily get without too much integration time. So we went for the microshutter array. And you can see exactly the same thing as what we saw with NIRCam. These older stellar populations that did not show those bright green or bright red features, you see very little evidence of emission lines. This is just sort of stellar continuum. This is evidence of an older stellar population. This is something that's going to be more like a protoglobular cluster, formed all of its stars and is now just sitting there. Meanwhile, this other region of the galaxy is this green spectrum down here. This is a younger, actively star-forming region where we have this booming O3 and H beta, nice strong H alpha line, plus a bunch of other nebular emission lines that are kind of dwarfed by O3 and H alpha. But very different populations within this one galaxy. So we're really sort of not just seeing, an entire galaxy squished together. We can start picking apart, where did things form and when did they form at different times. So that's very exciting. The other really exciting thing about this particular arc is that it does have a lens star. So this is a plot from the HST discovery paper of the lens star. All of these spaghetti noodles here are critical curves from different lens models. This is where the magnification diverges. And you can see in this little inset here, all of these spaghetti noodles fall right on top of this clump, which means that it has a magnification just from the cluster models of thousands. So this is something we're seeing thousands of times brighter than what it would normally be in the source plane, and thousands of times smaller in area than what it would normally be. It remains unresolved in the JWST image that we have over here on the right. Meanwhile, these two clumps on either side now appear marginally resolved, though it's a little hard to tell in this small image. But the fact that that is still an unresolved point source in the middle means that this lens star has a radius of less than 0.02 parsecs, which would be about 4,000 AU, which is how we really know that this is something so compact. It can't be something like a star cluster. This is how we determined that this was a lens star. Again, here, JWST has given us much more information. Hubble gave us the discovery. JWST gives us a lot more information about what we're looking at. From NIRCam, we were able to see that already a one-star fit to this, to the SED, gets a little bit challenging. We have this blue UV slope, and then we have a Balmer break here in the redder filters. That gets tricky with just a single star. So it was sort of hinting that there might need to be two stars involved here, a cooler and a hotter star, to give you both of those features. We do have a NIRSpec spectrum for this object as well. We are still actively analyzing it, but it seems to match the NIRCam photometry, which is good. The two instruments are doing what they should, measuring the same thing. But it really seems like that multi-star option seems to be more like what we would expect, or more like what we would be getting here, which is not unexpected since it is a very massive star. Those tend to come in binaries. So very interesting, and we are continuing to work on this. For the last couple minutes that I have, I'm going to pivot to some Cycle 2 projects. This one just got data a couple days ago, so this is hot off the presses. This is the Redshift 10 ARC SPT 0615 JD. This is what we saw with Hubble. This is the HST F160 filter. We were able to model this and measure that each of these clumps here is about 50 parsecs, give or take a bit in radius. And you can see that they're, semi-resolved, but there's obviously more structure there than what HST can measure. This is what we see with JWST. This is the same arc. It's much more spatially extended in the faint wings than what we saw with Hubble, which is really cool. And all of these clumps you can now see pop up much more clearly. These are, in fact, multiple objects here, multiple substructures that were just not resolved with Hubble. So, like I said, we just got this data a couple days ago. I can't say a whole lot more about it, but stay tuned in the coming weeks. We should have a lot more information to say about this. And it's a very exciting object. We will also be getting near spec for this in probably about 6 months. For the last 2 minutes that I have, I also wanted to mention the Legos project. This is something that I'm very excited about. As Jane mentioned previously, this is going to be getting imaging and also IFU spectroscopy of a variety of lens galaxies. What's really exciting here is that with that combination, we can pick apart the galaxies at a clump-by-clump scale, and not just get photometric SEDs on these small scales, but we can actually get spectra. We'll get IFU prism observations and also medium or high-res gratings, so we can get full wavelength coverage with the prism to get something like stellar continuum, but then use those gratings to pick apart the emission lines in the most interesting regions. And really, drill down on the physical conditions of these galaxies with those stronger emission lines. One really exciting science case for this is that this is a plot of stellar mass versus age. One of the big challenges with SED fitting is that ages can end up being fairly poorly constrained with traditional photometric SED fit, just because there's degeneracies between age, dust, metallicity, etc. With the addition of the spectroscopic data in a spatially resolved way, we'll be able to recreate a plot like this, where each of these data points is a small clump in one of these lens galaxies, but with much tighter constraints on these ages, and also stellar masses, other physical properties. We can really start to pick apart, what are these clumps in distant galaxies doing? How are these galaxies forming, evolving, forming all of their stars? And all of these are at about cosmic noon, so really, diving deep into the underlying processes driving the peak of cosmic star formation. So I'm really excited about this project. It's going to be getting data in a few months, so stay tuned. We'll have some really cool results coming up there. I'm just about out of time, so I will leave you with my summary, and thank you.
Awesome. Questions? Okay.
Thanks, that was fascinating. Can you comment on the masses and the sizes of the clumps that you're finding in the sunrise arc?
Yeah, so the sunrise arc, I don't know if I have the masses on hand, but the sizes are typically, like I said, scales of less than 10 parsecs. The masses from the Hubble photometry were, I think, sort of around the 10 to the 5, 10 to the 6 solar mass range in stellar mass. That was, with the somewhat limited HST wavelength coverage. So we are working on updating that with JWST, especially now that we have the spectra to get better estimates. So that will be forthcoming soon.
Modulo all the uncertainties in the SED fitting, which we know really well in the local universe, can you, for these clumps, are they consistent with a single aged population? Can they be made consistent with a single burst? For
the sunrise arc? So for the sunrise arc, they do appear to be consistent with a single burst. In particular, the spectra that I was showing, where is it? So like this one, for example, seems on first glance to be fairly consistent with sort of an instantaneous burst, and then you just let it evolve for a little while after that. We're still sort of going through all the rigor of that, so I can't say with absolute certainty that that's all it can be, but that's what seems to be the best fitting result so far.
So in one of your earlier slides, I think you showed a galaxy called Banana Galaxy. Yeah, this one.
Called it a banana. It's not actually called the banana galaxy. Though we could call it that, I suppose.
So here you show the variation of 4363 by 5007, which is indicative of the direct method electron temperature, so direct method abundance. And we do see a clear variation. So what order of magnitude in oxygen abundance do you see? Does it ensure chemical inhomogeneity within this banana galaxy?
In the variations, we don't have that just yet. This is still a bit preliminary. We're trying to clean up the fits and make sure we get the best possible measurement before we go through the calculations to get the abundances. So I don't think I have an answer for that at the moment of how big the abundance gradients are. But that should be coming shortly. We are actively working on it.
All right, let's thank our speaker again. All right, our next speaker is online. Adelaide, are you there?
Yes.
Hey, all right, let me do this one-handed.
Can I share my screen?
Yeah, 1 second. I need to stop sharing. Oh, good. Great.
Okay. Do you see the slides?
Yes, give me 1 second to make it full screen. All right. Next, we have a talk about resolving star-forming regions at high Z and lensed fields with JWST. I will, when you end a sentence around 2 minutes, give you a warning. And go for it.
Okay, thank you. So my name is Adelaide Clessens. I'm postdoc at Stockholm University, working with Angela Adamo. And before to start, I would like to thank the organizers for giving me the opportunity to give this talk from Sweden. So I will present what we can do when we combine lensing on JWST to resolve compact star-forming regions in high redshift galaxies. So as you may know, and it has been introduced before, HST observations of distant galaxies have shown that the morphology of high redshift galaxies is dominated by clumps. And these clumps that you can see on these images can be defined as compact star-forming regions, which affect the process of galaxy formation and evolution. And in these observations, the clumps are mostly giant structures at kiloparsec scales. And that is because with HST observations, without any lensing effect, we cannot resolve structures smaller than 500 parsecs at high redshift. Therefore, it was really difficult to say if these giant clumps were real or if it's smaller clumps not resolved. So using lensing effect, if you lens HST data, Mesh-Trick 22 built the first statistical sample of high redshift clumps with 166 clumps with the HST observations of lensed galaxies. You have on the left here the size distribution of the clumps. And one very important result in this study is that almost all the clumps are smaller than these 500 parsec limits we have without lensing. So it means that the clumps are smaller than what we observed before, which is a very important result because it means that resolution really matters for the study of clumps. And more recently, on the right, Mesa et al. Studied 3 high redshift strongly magnified galaxies, so you have 2 here, and showed that when we increase the resolution by increasing the magnification, we detect significantly more on smaller clumps, and some are very small, down to 20-30 parsecs with HST. So these HST lensing studies showed that combining spatial observation with lensing is really necessary to resolve these clumps in distant galaxies, and that these galaxies are not dominated by kiloparsec scale structures, but more by 100 parsec scale dense clumps with some very small ones. However, HST observations are still limited by resolution and sensitivity, and it's really difficult to build statistical sample. So if we move to JWST observation for this science case, we can now detect more galaxies and, of course, but also improve the clumps detection on already known targets. So I show here one galaxy at redshift 1.14 detected in the HST data of the cluster Abell 2744. And if you look at one of the blue clumps and we move them to the JWST data of the same galaxy, NIRCam images, you can see the big improvement of NIRCam to detect fainter and more compact clumps. So thanks to the first observations of James Webb, it has been possible to collect more high redshift clumps to really dissect the star formation in distant galaxies, down to very small physical resolution, and even down to, as Brian said before, individual star clusters in the early universe. So very good results have been obtained with the 3 clusters I show here, in which we can detect hundreds of high redshift clumps down to parsec scale, and I will highlight very quickly results from 2 of these clusters. I will just skip the sunrise hours because Brian presented it just before. So first, 1 year ago, we used the very first image of the Lansing cluster SMACS 0723, and we immediately identified a lot of very small structures within distant galaxies. So in Clessens et al. 23, we zoomed on these galaxies, so it's not all the galaxies we studied, just a sample, and built the first sample of James Webb lens clumps to study resolve high redshift star formation processes. So we use these first samples to investigate on the nature of these clumps. So I show here on the right a plot of size versus surface density of the 223 clumps we extracted from 18 galaxies. And we detect clumps from few parsecs to 300 parsecs, with the y-axis, in size and very high densities. If we compare it with typical densities of local star clusters, which are indicated with the 2 horizontal lines, these clumps appear as dense stellar structures that share many similar properties to local massive gravitationally bound star clusters in the local universe. And then if we draw lines at 10 parsecs and 100 parsecs, so it's a pink vertical lines, we see that some clumps present also sizes comparable to local star clusters, and a significant fraction of these clumps are smaller than 100 parsecs with James Webb data. Then if we focus on individual galaxies from this sample, like this one, which maybe you know, it's called the Sparkler galaxy at redshift 1.4, and we witness in this galaxy a rich variation of star formation events, as you can see with the color variations of the clumps here, and the distribution of ages, which go from 10 million years to a few gigayears. And this galaxy is really special because we detect also in the Earth, so it's all the circled clumps on the left image, clumps which are believed to be globular or star clusters. And this galaxy is a very good example of the capability to detect and study star clusters properties at high redshift with Lansing and James Webb. So this first study shows that the unprecedented sensitivity and high resolution power of James Webb is really a key factor in the detection and analysis of compact stellar structures as small as individual clusters. But what is now the next step? And the next step is to build a statistical sample of those clumps. To increase statistics, because we really need statistics to constrain simulation, for instance, or study redshift evolution of the clumps properties. So to do that, we are now using the NIRCam images of the Frontier Field Cluster Abell 2744 from the Uncover program that Akim presented before, in which we can detect thousands of lens galaxies. So in the dataset, we detect already by eyes a lot of very clumpy galaxies. I show here a selection of clumpy galaxies from this cluster between redshift 1 and 10, and the diversity of morphologies and colors indicate a large variety of star-forming events between the galaxies and also within the galaxies. So we selected 510 galaxies from the catalog published by Weaver et al. 23, with redshift between roughly 1 and 10. And I show here on the bottom left the redshift and magnification distribution of the selected galaxies. And on the right, the histogram presents the mass distribution of these galaxies. And we see that we detect very low mass galaxies at redshift mass 10 to 6, 7 solar masses, which are mostly the higher redshift galaxies in the sample, and very massive galaxies, so up to 10 to 11 solar masses, which are the lower redshift evolved galaxies in the sample. So then we detected clumps from these galaxies. So now going on the clump scales, we detected in this galaxy a little bit more than 2,000 individual clumps. So it's 10 times the size of the SMACS sample, so it's really an improvement of the statistics. We have this redshift distribution on the left with 35% of clumps with spectroscopic redshift. And on the right, I show the number of clumps per galaxy, and as you can see, we have very clumpy galaxies at redshift lower than 3. with maybe 20, 30, 50 clumps in one individual galaxy. So we extracted the photometry of these clumps in the different JWST filters and measured their properties using different SED fitting codes. And we are currently working on 2 papers on this sample, one focusing on the clumpy galaxies with redshift below the 5.5, it's Clessens, Adamo et al. In prep, and the other one focusing on the very high redshift clumps. I will not have time to present all the results we can have with these samples. I will just highlight some of them. So one first result is that we get the size vs mass distribution. So it's size on the y-axis and mass on the x-axis. And the points are color-coded by the pi parameter, which is a parameter we use to indicate if the clumps are evolved or unbound, it's red colors, or unbound structures in blue, which could also be due to the fact they are very young and not yet evolved enough to get bound. So we observe a correlation between mass and size, and when we fit this correlation, we notice that the clumps follow a relation with the same slope as do the local massive clusters. So it's a dashed line, but rescaled at bigger size. Then we see that fraction of these clumps presents similar properties both in size and mass than star clusters. So we detect very dense and small and evolved structures in this sample. And thanks to this sample, we will be able to compare the clump's mass function and density function with simulation and also study star clusters population in the distant universe. Now, if we focus on the age of the clumps, which is and if we divide the sample in redshift bins, so I divided in 5 redshift bins with almost the same number of clumps in each, we see a clear trend with that lower redshift galaxies present more old clumps, which is quite logical given the age of the universe as redshift 6. But why we do that, what is interesting with that is that simulation predicted that clumps should be disrupted by feedbacks or migrate toward the center of the galaxy, and that should not survive longer than 300, 500 million years. But here we detect clumps which survive longer than 500 million years, which is a very important result because the simulation predicts that only very dense clumps could survive, and this survival timescale depends on the feedback recipes implemented. So with this result, we can directly constrain the feedback recipes used in the simulation to reproduce this age distribution.
2 minutes.
Yes. And we can also study the migration scenario I just explained by testing if we can observe or not an age gradient within the galaxy. For instance, that the clumps will become older toward the center of the galaxies, which could support this migration scenario of the clumps. So we measured the galactocentric position of the clumps in the source plane, so without lensing effect, in these 5 redshift bins. And we plotted this clump's age versus galactocentric distance, and we do not see any clear trend in any of the redshift bins. However, when you look at individual galaxies, so in average we do not see any trend, but if you look at individual galaxies, that is not always true, and we see trends for some galaxies. So I present here 2 examples. On the left, it's a spiral galaxy at redshift 2.6, and we do not see any trend. We detect old and young clumps everywhere in the disk. However, on the right, we see a clear trend that clumps become older towards the center of the galaxy. So we have to explore deeper the data to conclude on that and understand for which galaxy we see or not indication of clumps migration. And if clumps migrate, then they can contribute to the formation of the protobulge of their host galaxies. So then here are my conclusions. So thanks to the first large sample of high redshift clumps, we can say that combination of James Webb and lensing, we opened a new window on the star formation, high redshift star forming processes, such as clumps and star clusters. We can constrain a clumps formation scenario. We can study small scale feedbacks in galaxy by getting age and density of the clumps. We can study the migration of the clumps, so the galactic bulge formation, and the role of star cluster in galaxy assembly and evolution. And I will just mention at the end future James Webb program. I will not mention the GLIMS program because Hakim did it, but I will just highlight this NIRSPEC program. So in this NIRSPEC Cycle 2 program, we will get NIRSPEC IFU observation and NIRCam data also for 3 high redshift, redshift between 4 and 5, highly magnified arcs. You have this here. And with this data, we will be able to study very precisely the properties of these clumps down to a 10 parsec resolution. And that's all.
All right, thank you so much. We have time for one question, burning question.
Hi, I'm Aklan from University of Florida. Thank you for an interesting talk. So I was wondering, as a theorist not familiar with observational techniques, how did you constrain the survival time scale of these clumps, given that you have one image?
Yes, so we used all the James Webb filters we have, and it's SED fitting.
Thank you. Any more questions, please go find her on the Slack and ask them there. Thank you so much again. All right, now we have our poster sparklers. So let me get that up. Play from start. There you go. Okay. All right. Let me. Oh, I'm not sharing screen. Am I? Can you see it? All right. Let me fix that. How does Blue Jeans work? There we go. All right. We want this one. Okay. Can you see it now? Awesome. All right. So we're going to do the poster pops. Same as usual. If you see your name, start heading up here. Let me click. Okay. All right, next, first we have Nicholas. Are you Nicholas? Hello. All right, I'm going to give you 2 minutes, and I'll have an alarm go off. So, all right, where are you? Sorry, where's my mouse? All right, there you go. Go for it. You need this.
Hi, my name is Nick Martis. I'm a postdoc at Hertzberg Astronomy and Astrophysics, working in the Canucks collaboration. And my poster is looking at the spatial distribution of compact sources in the SMACS 0723 galaxy cluster. So the first thing I've done is to create a model of the bright cluster galaxies and subtract their light out from the image. And after we've done that, we do source detection to identify 2 classes of compact objects. So point sources we consider to be globular cluster candidates, and then resolved sources we consider to be candidates to be cluster dwarf galaxies. And so the middle panel here is showing the spatial distribution of those 2 classes of objects against the top on our model of the intracluster light, the diffuse intracluster light, and on the bottom is overlaid on the model for the bright cluster galaxies. So we then use the second NearCam module centered off the cluster to subtract off a background level of these compact sources. And that allows us to kind of uncover a corrected spatial density. And so on the top here is showing the spatial density of the globular cluster candidates. And you can see in the red is the overdense area. And you can see it traces the ICL light very nicely. And in the bottom is the cluster dwarf galaxy spatial distribution, which appears to be more centrally concentrated around the central BCG. And then the last thing I'll point out on the top right is if you plot the spatial surface density of those 2 populations against the surface brightness of our total cluster galaxy plus intercluster light model, you can see that both populations correlate very strongly with the light. So regions of high compact source density are regions where the both the cluster galaxy and cluster diffuse light are concentrated. All right, and then I'll be at my poster tomorrow to talk about it if you like. Thank you.
All right, hold on.
Hi, everyone. I'm Richard Pan, and I'm a PhD candidate at Tufts University working with Danilo Marcassini on quiescent galaxies. So Hakeem actually introduced Uncover really well, so I'll just quickly talk about the quiescent galaxies in Uncover. Part of the NERSPEC follow-up was to select quiescent galaxies above redshift 2 that we thought would be really strong candidates, using a combination of the color-color diagnostics as well as the specific star formation rate measurements that we got from the photometric catalog by John Weaver and the stellar population synthesis catalogs by Binji Wang. we found 30 really promising candidates. And of those candidates, I'm presenting 4 of them here. Please note that the second one is actually a previous confirmation by the GLASS team about a year ago. And all of these quiescent galaxies are really interesting because they exhibit really breaks, potentially suggestive of really old and extreme old stellar populations, consistent with downsizing. The fourth one is also interesting because there's really strong H alpha emission that's broadened, suggesting that there might be an AGN in the center of the galaxy. And so if you have any questions or would like to talk about the sample of quiescent galaxies, please feel free to find me outside. Thank you.
All right, so before we break, we have a quick announcement.
Hello, everyone. My name is Ori Fox. I am the project scientist here at the Space Telescope for the JWST Data Analysis Tool Suite, which is a GUI-based tool that's designed to lower the barrier of entry for wrangling some of these complicated JWST data sets. I don't care if you've ever used Python or not. If you're curious to learn more and whether this is good for your data set, please come by. I'm going to try to get a poster at the coffee. If not, I'll have a table and I can at least show you how to get started on your own machine. And if we need more time, we can, contact each other through email. So I'll be in the coffee. Please come up and learn more about it.
All right. So plan to be back here at 3:30 at the latest, ideally 3:25. See y'all then. There's also a photo taking place at 3 right now. Never mind. We have a photo right now. And then you can have coffee. Outside for photo. Go outside.